Hello everyone, and welcome to the video recitation for data structures and algorithms in a nutshell. Today we're going to talk about Dijkstra's shortest path algorithm. So before we do a problem, let's start with some quick review for weighted graphs. Weights can be used to represent quantities such as distances, costs, or time. The weight is represented by a number which is on the edge in between two nodes. If the weights are not specified, we assume that the weight would be 1 for all. So that would mean that there would be no 10 here and it would just be a line. Since there is no number, we can just assume that it would be 1. And we're going to use an adjacency matrix to represent the weighted graph. So the problem, find the path between the origin and a destination such that the sum of the weights along the path is at a minimum. So there are many applications to this, and the one that I like the most is robotic navigation. And here's a quick animation that I found on Wikipedia, which actually illustrates it very, very nicely. So if we have our origin here and our destination, we're trying to find the shortest path between the two. And there's a barrier in between. So the algorithm which we use is Dijkstra's shortest path algorithm. And what it is it finds the closest path from the origin and then sees its closest paths. And we traverse through the graph looking at the shortest paths from each one and keeping track of it. So once we traverse the full graph and we find our destination, we are then able to know the shortest path. It might be a little bit confusing, but we'll go through a problem and it's fairly quite simple. One thing to keep in mind though is there's quite a lot of bookkeeping. So that means that we have to constantly keep track of the visited nodes, unvisited nodes, and update the closest nodes. So those are just words. Let's get into a problem. So we have our graph here and we are asked to find the shortest distance from node 1 to all the other nodes. The first step is to create an adjacency matrix to represent this graph. So we'll begin by writing down all the nodes. We can safely assume that the distance to a node to itself is 0. From here, what I'm going to do is I'm going to look at where each of these nodes can traverse to. So for example, for 1, I'm going to see where it can traverse to, which is 2, 3, 5. And then I'm going to mark the weights under each column. So 3, 5, infinity, 6, infinity, infinity, 0, 8, 4, infinity, 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 3, 0, 10, 11, infinity, 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 0, infinity, 2, infinity, 4, infinity, 7, 0, infinity, and 4, infinity, 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 1, 0. So now we have our representation in the form of an adjacency matrix, so we understand where each node can go to and the weight associated. So I'm just going to move this to leave enough room. And as I said, this algorithm involves a lot of bookkeeping. So I'm going to use this chart where I have the node number, where I have the visited node numbers here, the unvisited, the current, the distance to the current, and this will keep track of the shortest weight for each node. So 1, 2, 3, 4, 5, 6. So the first node is 1, as stated in the question. So we're going to visit 1. The rest are going to be unvisited. Distance to 1 will be 0, and I'm just copying it straight off of this chart here. 6, infinity. So now, of all of this, we're going to look at and see which is the closest node, and we've already visited 1. So the closest node is 2, because it has the lowest weight of 3. So now we're going to go and we're going to visit it. So 2, and 1's already been visited. 3, 4, 5, 6. Current node is 2. Distance to current is 3. Since we already visited 1 and we're visiting 2, that's the shortest, then we continue. So 5, infinity, 6, infinity. So what did I just do? What I did is I looked at, actually I made a mistake here. That's a 7. So what I did is I looked at the shortest distance to 3. So I looked at 2, and 2 cannot go to 3. Therefore, 5 is the shortest distance. 2 can go to 4, so the distance to 4 is going to be 3 plus 4, or 3 plus 4, which is 7. 6 carries down, and the infinity carries down. So now we continue our algorithm. So we already looked at 0, we looked at 3, we look at the shortest distance, which is 5. So now we're going to visit 3. So 1, 2, 3. Unvisit is 4, 5, 6. Current node 3. The distance to current is going to be 5. 0, 3, 5 carries down. From 3, we can traverse to 2, which doesn't make sense because it's closer to travel to 1 at 3. We can travel to 4 at 15, or we can travel to 5 at 16. But for all of these, 7 and 6 is less. So we carry those down, and we still can't travel to 6. So from there, we're going to look at the shortest, which is 5. So we're going to travel to 5. 1, 2, 3, 5. We haven't looked at 4 or 6. The current one is 5 with the distance to 5. So we're going to carry down 3, 5, 6. The distance to 4 when we're at 5 will either be 6 plus 7 or the original 3 plus 4. Obviously 3 plus 4 is less, so the 7. And from 5 we still cannot travel to 6. So that means that we have looked at all of these, and 7 is our closest. So we have 1, 2, 3, 4, 5. We still haven't traversed 6. We're currently at 4. The distance is 7. 0, 3, 5, 7, 6. Finally, the distance from 4 to 6 is 2. So we can add that to our 7, and we'll get 9. After that, we have found our solution, since which we now can look at every node. And our distances are 0, 3, 5, 7, 6, 9. So what that means is that the shortest distance to go from 1 to 2 is 3. So from 1 to 2 is 3. Or we can go from 1 to 3 with the shortest distance being 5. Or we can go from 1 to 2 to 4, shortest distance being 7. Or we can go directly from 1 to 5 with the shortest distance being 6. And we can go from 1 to 2 to 4 to 6 with the shortest distance being 9. And that's Dijkstra's shortest path algorithm. Thank you.